Distinguished Contributions to Satellite Communications Award from the Satellite and Space Communications Technical Committee of the IEEE Communication Society, and co-author of the paper that received the special mention for Barry Carlton Best Paper Award by IEEE TAES in 2023. Over to you, Professor.
Thank you. Thank you all. So if you had to read the whole bio, I would have given 2 lines, I think. So it's 5:30 in the evening, so thank you for taking your time off. So hopefully I won't put you to sleep. So as he mentioned, I got something in some award in satellite communications that was some time ago, and I gave a talk on satellite communications. Before that, I was doing something in game theory. We just gave a talk on game theory, and then so it just shows that how funding changes the way you do research. But something that's also fundamental in across all this, what is common for me is linear algebra. So probability, linear algebra, and the signal processing that we studied here, and that has carried us through all these whatever years of research in. So I think you're in a good place. Spend good time on linear algebra, probability, and signal processing, and it doesn't matter what the funding is, you will be able to handle it. So we start with some acknowledgements. One is the funding agencies, the European Research Council, and then the Luxembourg National Council for Research, and then colleagues at Spark, essentially PhD students and postdoc who did most of the work, and I'm trying to putting the slides. And we collaborate with a company called IE. They offer us practical problems in radar systems. So some of the collaborators have been quite helpful with data, with devices, with lab, everything. So some acknowledgements also go to them. So I have a book that we published a couple of years ago. Some of the talk, I wanted to center the talk around this book, but then I tried to change it a bit so that the book is anyway there. It's been cited. So I would start with what does modern radar systems look like, and then I'll look at predominantly single input, single output radar waveform design for the 45 minutes or 1 hour. I think we have sufficient time only for this, and then I will not go into a lot of math in this one. So either the papers or in the book you'll have all the math. I'll give some examples trying to motivate from the practical problems that we have. And then if time permits, I will touch upon the MIMO waveforms, MIMO radar waveforms. Essentially, you will see that some of the aspects are pretty much similar to the communications that you have been looking into, and sometimes they differ a bit on how things are with the communications. So the radar origins, well, we start with the experiment proof of electromagnetic waves. But the fundamental contribution, again, a couple of last week or the week before, you had the millimeter wave radar by ATI with Sandeep being the thing. So the millimeter wave generation, I think the credit should go to Jagdish Chandra Bose. And then, of course, the other thing that helped us was the radio transmission by Marconi. And the first radar was called the telemobiloscope, and then it was just used for detecting and ranging. So that's what the radar is the acronym for, radio detection and ranging. But now radar is now no longer an acronym. So everybody is using radar as if it's an English word. So that shows the proliferation of radar. So essentially, this is how the radar has evolved. So from these large arrays to detecting missiles or aircraft at 500 kilometers to something that if you look at this one, this is an Infineon radar. These are some of the radars that we have now in the lab available at $200 maximum. So these are small form factor. Of course, they cannot detect anything beyond a few meters, but then the applications are also different. So we're not looking at missiles at 500 kilometers, but it's something much more closer to the radar. So the size has come down, the cost has come down, and then if you think of it, maybe the capabilities or the way that you are using the radar has also changed. So these are a number of things that we are using radar in. I try to give some things that we do in our lab as a motivation. One thing that we have is people counting. I think also here, but also in Europe, it has very much important that you don't see the face of any person in any of the, unless you clearly mention that you are doing the videograph. So there's a lot of privacy associated with it, but and also you need to have some security aspects. So you need to count how many people are there in the room for various things, right from simply to switch on the AC or try to set up what is the temperature of the AC, and then of course if somebody who's not supposed to be there is there. So one thing that we are trying to do is to use multiple radars to set this up. So here's, yeah, so you could see the radar locations here, and then you will see the people walking. That's the camera version, but then the dots are the ones that the radar sees. And then if you fuse the radar aspect, so you will have 3 radar sensors, and then you could see the track that the person is following. So you can count how many people are there. You can count how many, what they're doing. The important thing is that in an indoor environment, you will see that people cross each other. So there's occlusion. So if you have put one radar, you probably not see 2 people, one behind the other. So you need to have some diversity in that case. So the other one that we are looking at is vital sign monitoring. So you want to check the heart rate, the breathing, essentially the heart rate variability, etc. for multiple applications. One being for the autonomous vehicles, where the concept means that the driver has to take over the vehicle in case something happens, and the driver has to be alert. One way of looking at the alertness is checking the breathing and heart rate, and this they want to do it without any contact, and then the radar is one that is being used for this. Here is a quick thing that we did with IE. So the student is using an apparatus, a shirt that has radar, that has breathing sensors mounted, and then he has this is the radar. You see, this is the radar that he's used for measuring, and then you can see once he is starting, let's blink. Okay. So what you see is if you look at, this is the chest wall displacement that the radar measures. And then if you look at the units, we are in millimeters. Okay, so this chest wall is being measured on top of the clothing that you have, but you have to measure you have to distinguish between, which is 4 millimeters, 3 millimeters, 2 millimeters, so on and so forth. So that is the kind of resolution that the radar requires. Now, it was not necessary for a missile that's coming far at 500 kilometers. You never had any concept of that resolution of millimeters, but in these kind of applications, the resolution becomes important. The other thing that becomes important is that now he's not moving his arms, he's not moving anything else. The time he starts moving his arms or his head, or he starts shaking his leg, things change, because the radar is picking up the information from all the moving parts. While you are interested in a particular thing, all the other things are sort of not necessary. They are somehow have to be filtered, or in the sense that the radar's processing should have what we call low side lobes. These are the ones that are not in the main lobe of the radar, but in the side lobes of the radar. So you should have quite low side lobes. So these are some of the requirements that we would have when we sort of try to look at the modern radar systems. I don't know, I should use this. Okay. So the other thing is the radar. Yeah, of course, if the radar is the only sensor, I would be very happy, but radar also has to go with other sensors. The biggest problem with radar is it does not, like camera, does not give you any semantic information, and unlike LiDAR, it does not have the angular resolution. Still, we are stuck with 2 antenna, 4 antenna radars. Maybe now we have 48 by 48 radars, but you don't have 48 digital channels. So you will not be able to get such a kind of processing. So you would need to fuse radar and LiDAR. So LiDAR cannot distinguish metallic objects. It just gives you an image. here is a person who's coming in, so you don't see any metal on the person, and then somewhere somebody should have some metal. Yeah, these are LiDAR and radar images put on one top of the other, and then you should see here that you could see the very high reflectivity because of the. So here the fusion is such that the LiDAR focuses the radar, gives information to the radar to focus on energy on a particular region. The radar beam forms, and then you will get the information. Okay, so and then another important problem that we now have is that radar at some point in time was a luxury item on a car. Now radar is more like a utilitarian item on a car. The cars not only have single radars, but they have multiple radars in the front bumper, rear, side, everywhere. And then unlike the communication system, there is no protocol in radar. So nobody suggests that you should use this frequency. I mean, you have the ISM band or you have the band, but nobody has any sort of time division, multiplexing, frequency division. Nothing is available in radar. So everybody transmits on their own. And so you would have interference. For example, in this case, let's look at the simple example. Here the vehicle is, this is the front radar of the vehicle, and then it is going to interfere. So then you have the rear radar of the vehicle in front. And then what happens is that this vehicle is supposed to detect some other target. So it is a two-way propagation for the radar of this vehicle. So R square loss in one direction, another R square loss in the other direction, roughly R power 4 loss for the radar here. But for the radar that is transmitting here, you have just an R square loss. So the interference is going to saturate the receiver front end unless you take care of it. So this is something that is also happening, the interference in, at least from an automotive sector. So you need to understand how to design a radar system to handle the interference. So one thing is you have to handle the interference. The other thing is you need to have quite high resolution, and then you should make sure that you don't pick in unnecessary things that are not in the range that you are looking for. And then the third thing is that single radar is not a solution. You would need multiple radars and multiple sensors. So we will not touch most of some of them, but we will look at some simpler things. So what is happening now is you have short range or shorter range, and then you have non-stationary targets. So you had, for example, I keep going back to the missile or airplane. So it was guided by kinematics. It was a rigid body moving in. By here, you're focusing on human beings, for example. So the left arm could move independently of the right arm, and then you could shake your head, nod your, nod your head, shake your legs. So kind of things become, to some extent, non-stationary for the radar at least. Maybe in your mind you know what you're doing, but for the radar it is non-stationary, and the resolution is very high. Unfortunately, we don't have the capability still to get the good angular resolution. What we have to do with is good range resolution. See what we can do with the range resolution. And then you would probably have multiple potentially uncoordinated systems. So if you think of it, the radars that back in time were big. They were just big to make sure that you get enough SNR, but the processing was simple. But now the radars are small, but you need quite heavy processing to get whatever you need to get from them. Okay, well, is it so bad? No, you have some degrees of freedom that you could use to address some of the problems. One of them is you will have multiple antennas, so you could have different waveforms that you can transmit. And then you have multiple sensors, you know how to fuse them. And of course, you have all the receiver processing algorithms. You can use AI if you want. All those things that would help you to sort of get some radar tasks done. So I will quickly go through this radar classical pulse Doppler processing. So you know that you would transmit something from the single antenna. So it's a pulse, repeated pulses. We repeat so that we get some information on Doppler, you get some other information. And then what happens is that this is emitted into the environment, and then the targets interact with this electromagnetic wave, and then some of them are backscattered. So you would backscatter from different paths, similar to your multipath propagation in the communication. And then you would have a delayed version of the transmitted pulse, and then of course you will have the Doppler. And then what we're missing here is the link budget, which gives you the power loss, which is typically R power 4. So there are some design trade-offs. So if you look at it, so you would have, you need a radar typically measures the range, Doppler, and then the reflectivity. You saw that the person with the metal had a much stronger reflection than otherwise. So that is the reflectivity. So, and then to get all this, it has some parameters that it need to design. One of them is high range resolution. It means I need to distinguish with small differences. It's more like a CDMA that we had very small pulses. So you need to have short time transmissions or large signal bandwidths. Doppler resolution, it means that you need to dwell on the target. You need to illuminate the target for a longer period of time. And then the other one is the angular resolution, which you basically require a lot of antennas. So there is a trade-off here very clearly that if the target is moving fast enough, then if you focus the target only on for long dwell times with the Doppler, then the range is changing. So you would have some sort of range migration becomes a problem. Okay. Sorry about that. Okay. So very quickly, so this is the basic thing. You have a very short pulse. It has a very good range resolution. I send a nanosecond pulse. I can always distinguish between two events that are nanosecond apart. Okay, so that is the good thing. But then the average power is very limited, unless you blast a lot of things. And then as I said, it's a R power 4 loss. So you would have very limited SNR at the receiver to do any sort of detection. So the average power proportional to pulse width. So if you increase the pulse width, you will have more power. You can integrate the power. You get more SNR, but then the resolution is inversely proportional to the pulse width. So that requires is the first dilemma that we saw. We try to see you need to have the energy of a long pulse and the resolution of a short pulse. So that is what leads to the waveform. I need to design something that can have good energy, but then also give me good resolution. Okay, you could do waveform is essentially something like a structured modulation of the basic pulse in time, frequency, or also in amplitude. So this is a very simple square pulse. So you get a continuous wave of some time t. And then this is the time t, the bandwidth is 1 by t. So the time bandwidth product, which we keep referring to, will be 1. On the other hand, you have in the TI wave chips, they use the linear frequency modulated waveforms. So you start with one frequency, and then the frequency gets wrapped up to another frequency. So the frequency uses delta f, the time is t. They don't have the inverse proportion relation. So you would have some time bandwidth product. What we are going to look at also is what we call the phase coded waveforms, more like your CDMA spreading codes. So you have a pulse width, you split them into small chip times, and then you have different phases on that each of the chip times. You could have binary phase, just 0, 1. Something like your gold code could also be a good waveform, and then, or you could have multi-phase things. So here you would have a different time bandwidth product. So if you for a given pulse duration, if you increase the number of chips, this time of the chip reduces, so you would increase the time bandwidth product. So critically in radar, so you would always, they don't ask what is it what each of them is individually, but then you look at the time bandwidth product. I think you've also seen this, the ambiguity function. You have a transmitted waveform in the absence of noise and in the absence of any interference. This would be the, okay, I should have put a minus t here, minus tau. So you would have a received waveform which is delayed and then Doppler shifted. And then typically, if there was no Doppler, the best solution for high SNR in AWGN, the optimal detector would have been a would have been a match filter. So that is the flipped and conjugated version of S of t. So I would use that as a received filter, and this is what we get as the ambiguity function. So this does not include anything else, it's just the waveform. If you look at the ambiguity function, you can get a lot of information about the waveform. How much is the range resolution, how much are the side lobe levels, what is the Doppler resolution. We'll see in the next slide. Ideally, what I want is that I transmit this signal, I receive another signal. So as when the signals are matched, I should get a peak, and when the signals are mismatched by any amount, I should get a 0. So essentially, it's a thumbtack response that I would like to get. So that is what it should have infinitely. That depends on the narrow spike at the origin, because if you look at this, this is nothing but the energy of the signal when the Doppler is 0, and then if you want a thumbtack, and if you want only at one point, it becomes an impulse. Okay, and then no side lobes and no ambiguities. So you will see why it is called an ambiguity function. So this is what happens if I just transmit a square wave. If I transmit a square wave, if you look at, if in the no Doppler, the 0 Doppler cut, if you take a square wave, you convolve with itself, you get a triangle. Okay, and then if you look at, this is the top view of the ambiguity function. So what happens here is, if you see, this is a delay, this is Doppler. So these are the contours. So if I change if you see the thing here, the delay Doppler contours are parallel to the delay axis. Okay. On the other hand, this is the one for the FMCW, frequency modulated continuous wave. It's nothing but a frequency ramp here. I think this would have a certain ambiguity function. If you look at the ambiguity function, you see that the ambiguity function is tilted. It is not parallel to the axis. What this means is that if I measure a delay at 0 Doppler, okay, and then I change the Doppler, I keep the delay the same, the target is the same place, or somehow the delay the same, and then if you change the Doppler, the measured delay is different. Okay, so there is what we call a range Doppler coupling. For example, here the delay, irrespective of what the Doppler was, the delay was the same. Here, as you change the Doppler, the delay is also changing. Maybe you can give it a thought. But so here there is a tilt. So for a particular delay, you should know at what Doppler it was measured. Okay, it is not just by itself. So there is a range Doppler coupling that is happening in this frequency modulated wave. I hope you get that. If I measure the delay at a particular Doppler, and then if I try to measure the delay at another Doppler, I would not get the same thing. The delay depends on the Doppler. Okay, so what we do typically is, that's why you would have you probably have seen that you will have an up ramp and a down ramp and these kind of things. So those are for these kind of mitigating these coupling issues. Nonetheless, if you look at this one again, if you look at maybe I have. Okay, so this is the S of t. Then you see this is a modulating. This is the frequency version, and then it is it has a rectangular pulse, and then you have S of t there. Okay, so if you know from our spectrum analysis that rectangular pulse has the shortest main lobe and has about 13 dB side lobes. So that is what happens here. You don't see the side lobes here, but then it has, probably in the next picture, it has 13 dB lobes here. Again, it's difficult to mention this, but then this happens. This is what is a typical representation of a FMCW signal. This is the frequency. The frequency is nothing but the differentiation of the phase. So the phase is FCT plus this sigma t square, and then differentiate, I would get a affine function. And then whenever you transmit and you receive, it would get, if it's a pure delay, it gets shifted along the time axis, either time axis, and if it's a Doppler, then it gets shifted along the frequency axis. Okay, so but then it becomes very difficult. For example, here you don't know whether it is the difference is because of time or because of frequency, because both are acting in tandem. Okay, that is the range Doppler coupling that we are looking at. Yes.
If the Doppler frequency has to be large enough that So basically, the Doppler frequency has to be large enough for the, if I'm looking at the range FFT or something like that, in the case of FMCW, the Doppler frequency has to be large enough for range bin of the target to be shifted to the other side, right? To the left or right bin, I mean. So even if there is a Doppler, then the range is still not shifting in that case.
I mean, you're now talking practical things. So if you write the equation, there is always range Doppler coupling. When we write the receive equation, you will always have range Doppler coupling. But the way we do, so we don't do up ramp, down ramp, all those things are not done. So what we assume is that the Doppler is very small. So the Doppler is very small, so you could neglect essentially the Doppler contribution to the range calculation and proceed. So that's exactly what. So that's the practical thing that we use. So you asked me why. Maybe I go to the next slide and then I come back and. Okay, so these are some of the things that we have when I have FMCW. You'll have a very small main lobe, high side lobes, 13 dB peak side lobe. It is reminiscent of a rectangular pulse, a very classical window that we use. That means that there is some aspect to the underlying waveform, which is the ramp, but then you also have some large contribution to the window that you are using. Okay, and then these are very classical things that we did in spectrum analysis. How do you reduce the side lobe? I window it. So when I window it, I reduce the side lobes because I taper it, but I increase the main lobe. Well, that's an unfortunate story. So what you could do is you could just do it at the receiver side. I get S of t. I transmit S of t as a rectangular pulse, but then at the receiver I don't use S of t. I use a windowed function of S of t. It's just one side. Then it becomes a mismatch filter. It's not a match filter, it's a mismatch filter, so you lose in SNR. Alternatively, you could do the windowing at the transmit side. Then it becomes an amplitude modulation. And then you always want the radar to be at the saturation of the amplifier, and you want always constant envelope, but amplitude will impact the amplifier efficiency. So, so this is what typically would look like. You would have an LFM somewhere, and then you would have all the other windows coming in power, and then also in this is in the spectrum, and then in the delay domain. So this is the classical problem with LFM, that you have range Doppler coupling, and then you have to do amplitude modulation to lose to get some sort of lower side loss, but you lose on amplifier efficiency. Other thing is you do windowing, and then you will have mismatch loss. Okay, this is in addition to the very fundamental problem that there is always a bias variance, or the main lobe increases to reduce the side lobes. So that is fundamental, that we cannot change. But the additional things that we have, the SNR loss, we have the amplifier inefficiencies, that's something that we can look for to change. So that is what we try to look for, go beyond ambiguity function. So beyond FMCW, and then we start looking at the phase codes. There are some phase codes called the Barker codes, which are binary codes, 1, 0. There are only few in number, and then they have they have the peak side lobe level, which is lower than 1/m of the main. This is by construction of the code, it can be proven. Okay. So this is one particular phase code, but nothing prevents us from looking at other phase code. We will look into it. But then the important thing is, okay, so if you look at it from the linear frequency modulated waveforms, all that you had to do was to ramp up the frequency. And then what do we have in your control? What is the slope of the ramp? There's nothing else that is under your control. You don't really have many degrees of freedom. On the other hand, if I want to do a phase code, I could put 1, 0. I have multiple ways of putting a sequence, essentially a sequence design. I can put in any way. So that should give you much larger degrees of freedom to address some of the problems that we mentioned earlier. Okay, if that is so easy, why not use it? The problem is here in FMCW, you receive something, and then you have to do the match filtering. So the match filtering is again multiplying by the S of t, its conjugate thing, and then continuing and then you would go into the digital domain. So if I do the here in the FMCW, you can do this de-chirping, which we call, or stretch processing, or the match filter. You could do it as an analog multiplier. Okay, and then when you do the analog multiplier, and then you do you sort of remove the high frequency, what you will have is what we call the beat frequency, which is somehow related to the time delay. Okay, and that amount of the beat frequency depends on the bandwidth. That's why we need, even though we sample at a lower rate, or the beat frequency depends on the bandwidth. So here is how the beat frequency would look like. Sorry for going back, I should have put it. This is how the beat frequency would look like. This is the actual range at which the target is. This is the speed of light. This is the bandwidth used, and this is the sweep time. Okay, for a given sweep time, the sort of you could see a larger beat if you have larger bandwidth. So even though by default everything is small, but the way you map the delay to the frequency is through the bandwidth. And that is what it governs the sort of resolution.
But in practical numbers, the beat frequency will still be, say, 100 to the bandwidth.
Yeah, it is very small. It is very small.
So the classical radar processing only requires you to sample at a rate which is maybe 100th or 1/200th of the bandwidth.
Yes.
Whereas if you want to do something like JFRC, then the communication receiver anyway has to sample at a rate that is equal to the bandwidth, but because it's a joint communication and radar signal, even the radar receiver has to sample at the communication bandwidth.
Yes.
So that is the cost that I'm referring to, that you can no longer build a radar at which can sample at 100th of the rate equal to 100th of the bandwidth.
Yes, if you're using the ISAC system with FMCW as an underlying radar waveform, then you are sort of, you have that problem.
Yeah, or any communication waveform, if it occupies a bandwidth of B and you're using the same waveform as a radar, and you want to do a monostatic radar like thing where you're aware of what is being radiated out, and so you want to use your knowledge of the radiated signal to do target detection using the same communication waveform, then you still have to sample at the communication waveform's sampling rate.
Yes, you
So
have to sample. So that's the hit the radar takes. So if you increase the bandwidth, of course, you are getting better in terms of resolution for the radar, and you get rate in terms of communication. But because you are doing it jointly, it has to, or
Correct.
you branch the processing. I don't know. You know, if it's you branch the processing, you have a communication processing at whatever rate you want to do the Nyquist rate, and this one you do the beat stretch processing.
So there, to do that, you'll have to insert an FMCW like subframe periodically.
Yes.
And there you'll take a hit in your communication rate.
No, but this specific thing is only for FMCW.
Correct.
And then I'll show the PMCW, the phase coded again goes back to the communication. So that gels well with the communication, not this one. And then even here, how do I embed a symbol in a frequency modulated scheme?
You can't.
So I either have to do an amplitude modulation of something, fine, but then yes, you could do that, but then the rate is very small.
Very small.
Very small. So
Not
then
worth
it doesn't really suit. So this one does not suit ISAC to a large extent.
No, but generally I'm saying that if you think of ISAC, you're getting the sensing capability or the radar capability, but at what cost? Instead, if you were to build a simple, every 10th frame you replace one OFDM symbol with an FMCW waveform, right? You're not really taking much of a hit on your communication, but you can still do the low rate radar processing.
No,
to
Chandra,
get the sensing
so then again, yes, So then it depends on what radar task you are looking for.
Correct.
So if you are putting, now you are putting every 10th symbol, you are essentially decimating by 10 the Doppler, because I would look at Doppler at every interval, right. So now I am getting Doppler here and after 10 frames and after 10 frames. So you have that decimation factor by 10. So even if this decimation factor by 10, you are fine with the Doppler, you are looking at stationary targets, fine. I mean, you might have to see how much you gain in lose in SNR, but still that is fine. But you are looking at something moving, maybe you lose in Doppler. And also there's another issue, which is the clutter, which is the thing that we have to remove, but that's another day. So we are looking at phase codes, and then this is the PMCW, the phase modulated phase coding. Unfortunately, in this, the match filter is again a sequence based, like the pilot things that you do to get the start of frame or whatever. So, and then this one has to be matched, has to be sampled at the carrier frequency or the bandwidth. Sorry, at the bandwidth. Okay. So here, you'll, for example, I give you the automotive radar, probably in the TI, they go from, one example is going from 77 to 81 gigahertz. So it's a 4 gigahertz bandwidth. Okay. You are not in FMCW, you are not sampling at 4 gigahertz at all. So the beat frequencies, as Chandra was mentioning, could be in order of kilohertz or megahertz. So you're sampling at that rate. And PMCW is basically you're transmitting at 77 gigahertz, and you have a receiver that needs to be, you need to do a match filtering, and you have to sample at that rate. Okay. So that is the problem with PMCW. You don't really have, again, if you think of it, I needed very high resolution. The resolution is inversely proportional. Resolution is proportional to bandwidth. Higher the bandwidth, better the resolution. So I really don't have a PMCW. There are one or two chips that did these kind of things at 77 gigahertz, but really not many available. So that is the drawback of why PMCW signals things are not so very popular. You really don't have many of them. Okay, so that is what the things. So, but PMCW offers large degrees of freedom. So we as an academics, we try to look at what we can do with PMCW. As I said, it offers a lot of degrees of freedom because you're designing a sequence. If you have an n length sequence, you have n degrees of freedom. What do I design this for? So if you look at the ambiguity function, we always go back to the ambiguity function. So the ambiguity function is nothing but a correlation of the waveform with the flipped and conjugated version of it, and then you would have a peak when you have the delay, and then you have all the side lobes. So we are trying to look at the autocorrelation function of the sequence, try to see how the autocorrelation function looks like, and then we would like to have the autocorrelation function to be very low except for the zero lag. So this is called the peak side lobe level. So you look at the maximum of the autocorrelation function, and then you try to sort of minimize it, or you take the integrated side lobe level, you take the energy in all these correlation lags other than the zero lag. That will give you the total power that is there in the unwanted region, and you try to minimize that. So all these things are obtained from the ambiguity function. That's why it plays a central role. And then you could have, of course, a lot of constraints, the peak to power average ratio, unimodularity. So you would want all of these guys to be on a unit circle, or it could have anything anywhere on the unit circle, or maybe you want to put them QPSK or some MPSK signal. So here is the important thing that we were trying to look at, why the side lobes and everything are important. So again, essentially it's a detection problem. So I have a primary target, I have a secondary target, I put a threshold. Somehow I find a good threshold, so everything is fine here. The target is above, the target response is above the side lobes. I put a nice threshold, I get 2 targets. In this case, the side lobe is quite high, and you know that the side lobe is high, and then you have a very weak target. Okay, so the weak target is very weak. So this is where the side lobe, this is actually the main lobe reflection from the weak target. So it is as good as your side lobe. So since you know your side lobe is quite high, you would put a threshold higher and you will lose this target. On the other hand, if you push the threshold lower, you will start having false alarms. You will see this as a ghost target, this another target. These are nothing but the side lobes from this target. So it becomes essential that if the side lobes are very small, then irrespective of how weak the target was, you could always detect it. So that is the idea that we are trying to see here with the peak side lobe level and the integrated side lobe level as two different optimization functions. Is the slide being circulated afterwards, or?
It's visible to the online audience,
Mm-hmm.
and it's being streamed on live on YouTube also.
Oh.
Is it,
No. I was trying to see if I can leave the slides and then do distribution afterwards. Okay. So these are some of the classical optimization problems that from the radar centric. Now we start going into the optimization. So these are some of the classical cost functions that you would do. The side lobe level, you don't use the zero lag, or you would use the maximum, the integrated side lobe level. The problem is that they are quite difficult. Some claim NP hard, but essentially they are difficult. So they are not nice convex problems or anything that you could use solve it and write the equations. And then of course you want to handle these problems in good time. So I would not go into all the details of these are some of the methods that are available. Gradient descent based methods, majorization, minimization, coordinate descent, ADMM, BSAM. Now there's been a lot of work on the BFGS based methods. They call limited memory BFGS, LBFGS. So every time you come up with a new algorithm, you can use it here. The theoretical aspect would be to sort of, it's all these are iterative algorithms trying to optimize not the actual cost function, but some surrogate cost function or some upper bound on the cost function, and then all of them always claim, you can always show that there is the monotonic decrease in the cost function, but this cost function is not the one that you really wanted. It's some function of the cost function, I would put. So you need to see how good is the solution. And then if you're mathematically oriented, so then you can also try to prove what is the convergence not only in the cost function but also in the argument. So how would that work in the argument? So I will not go into the details, but I think the book that it has, but then you could also look for many of the papers that are available. So I come back to this equation setting. We realize that there is this interference. And then I think there was also some discussion in the previous thing by Sandeep when they mentioned something about the interference. So here is what is the thing. So you have the victim's transmitted chirp. So this is what the victim transmits, and then there is an interference of somebody else who's using exactly the same FMCW, which is quite rare. Okay, even if you set up two devices to use the same settings, because there are two different hardware components, not exactly everything would be the same. So it would not be. It would be a very ideal situation that the other one is also using something quite similar, and then what the receiver would get is green. Okay, so now if I am the receiver, I don't know whether I got the yellow was because of a target or green was because of a target. Okay, so I'm going to see ghost targets in in my waveform. So this was the actual target. This is the interference, but the interference is also exactly like a return from the target. So I would see ghost targets, additional targets that I don't want to see. But that is easier. So at least you have your target and then you have another target or some of the other targets. But at least your target is still visible. On the other hand, this is something that we call similar slope, because there will always be some hardware imperfections that will not let everybody use the same thing. So there will be something similar. There would, but it's not exactly parallel, but there will be something similar. And then you have this other case, which is typically the situation where you have sweeping interference, where the frequencies interfere over a small period of time, not every time, but a small period of time. And this is how this one is just another target coming up, and this one is the similar slope. You see the range, there is the target here, and because of the interference, the output of your detector looks like this. The yellower, the stronger. So you don't see your target. At least in this, you could see your target. Here, you don't see your target. Okay. I don't know how to close. In this one, slightly better. You see here, but then you would see still a lot of interference. You could see that the noise that is coming out of this system is spread both in time and in Doppler frequency. Here, it's largely spread in range or in time. So how do I analyze, how do I proceed? So I cannot, it's a dynamic situation as an in an automotive setting. I cannot instruct, that there's no central authority to instruct everybody to use a particular FMCW code or FMCW signal. Everybody has to do it on their own. The best thing probably there is to do, everybody does randomly. So if everybody does randomly, then at least, you know, the chances of all of us hitting each other goes down. Weak law of large number, strong law, whatever law. So you get that. But then you would miss out. Then if I'm using a completely random sequence, it's a PMCW system. In a PMCW system, I would need to use a high rate receiver, high sampling rate receiver. So somehow can I reconcile between the nice properties of FMCW and the need to make it more random? So what we try to do is to sort of look at settings where instead of having one chirp within one period, you split it like a PMCW, you split it into number of smaller segments, and in each of the segment you would you could use a polynomial phase, which is like this. As a special case, if the polynomial is quadratic, you will have FMCW. If it is not quadratic, you will have different slopes, different phases. This is a polynomial phase system. In particular, if I just put quadratic, I would have the FMCW on a much smaller scale. Okay, but then all of these things could be randomly generated. So these sequences in the code are randomly generated. So every chirp could be different. Every chirp could have different coefficients for the equation, and so that is how you're bringing in the randomness. So instead of one chirp going, you split them into different chirps, each of them going around in different ways, and that randomness gives you the immunity towards interference. And then, but still, you still have these quadratic phases that you can run detector. A bit more complex, but you can still run it nonetheless. So I would skip the as I'm running late. I would skip the thing. So this is what would happen if I were to use this sort of waveform. Of course, there is an optimization involved in the waveform. Again, using majorization, minimization, and other things. So this is what, after all those things, you could see the target cleanly. Now you could say that this is still, I mean, statistically, this is what also we have seen, that the interference, this is how the interference would look like now for us. It is at least minus 14 dB lower than the interference that you would normally see in an FMCW signal. So you're getting the benefits of both worlds. It looks like FMCW, but also has the inherent randomness that would give you some immunity towards interference. We actually tested this on a system with the USRPs, but of course we did not transmit over the air. But what we did was to induce a delay, and then we sort of added it and looked at the spectrum analyzer. And then this is what if you look at frequency, you have a FMCW waveform that is transmitted, and then this is also the interfere waveform. The received signal would look like it, and then this is what I was trying to say. You will have your target, and you will have another interferer. Fine, at least you have your target. If I have the interferer waveform is like this, this is what I was trying to tell you. This is how our chirps look like in frequency. What you saw, all those curves, was in time. This is or the phase. This is the frequency, and then you see the randomness in it. But then within each portion, it is still linear. Okay, and then you would see the target. Of course, there is a slight increase in the noise floor happens. And again, if I use two, this is important, if I have two cars using the wavefronts that we designed, there is enough randomness that if you look at those two interferer also using a random thing and then the victim also using a random version, you would see still a good interference. So this is one thing that you should try to marry the PMCW and the FMCW and try to see if we can get something out of it. The last few slides I wanted to say what we are trying to do now is going beyond the linear frequency modulation, going into the nonlinear frequency modulation. The idea has always been the same. Want to have a certain shape in time domain. Essentially, I want to have constant envelope so that my amplifier is in a good shape, and then I want to have a certain shape in the spectrum. I don't need to have side lobes here or there. Okay, so I have a time domain constraint, I have a frequency domain constraint for the same waveform, and these can be independent of one another. So the question is very basic question: can I design a system where I can get both a constraint on S of t and a constraint on S of f independent of one another? Okay, so this is what you would have. You have a spectrum, you have the time domain, you have this sort of equation. There is a classical thing. So can I design both of them? So typically we don't know if we can design. There are some criteria, Paley-Wiener criteria on how the amplitude of one relates to the amplitude of the other and these kind of things, and then there is also the Hilbert transform relation for real signals. But as a general theory, as of now, we don't know if this kind of thing exists. So I want to have very nice side lobes with a very constant envelope. So what do we do? So we start. Let's assume that for this class, for this lecture, we assume that the spectrum is of this form. Very simply, of this form. It is nothing but if you choose different g's, you will get different functions. You could get the Han, Ham. You could get a different. If you look at it, this is nothing but a Fourier transform of something, right? So let's assume that the spectrum looks like this. With these g's are the parameters that you would like to tune to make this spectrum look what you want to look like. Okay. So and then the idea has been, I don't know if you are aware of this, the principle of stationary phase. So the idea here is, look at this one. This is an integral. This is an integral, and then there is a phase function that is coming in. And then the major portion of the integral that contributes, the major portion of the signal that contributes to the integral is when the phase is varying very slowly. Okay, so that when the phase is varying very slowly, that is what, or that neighborhood is what contributes to the integral, and anything that is varying rapidly gets cancelled. Okay, so if you look at, if you just take the sine function, sine omega t, you integrate, you get 1 by omega cos omega t. And then if you let omega to go to large, that means you are oscillating very fast, then your integral becomes smaller and smaller. So it goes as order of 1 by omega, right? Something like that. If the smaller the omega, the integral dies down very slowly, but then the same thing here, roughly, that what is important is the case where the phase is more or less stationary. That is the idea of what we call the stationary phase. So if you look at the frequency and so this is what if you look at, this is the frequency and the phase is I think so you're looking at only one portion of the signal. All these things that they change very rapidly, the phase changing rapidly, they don't contribute to the integral. So this is the idea that we try to use. We are not going to get an exact solution to our problem that this is an S of t, this is an S of f, and I would get what I want. No, I would not get it. I would get something close to it, but at least I can proceed and get something that is meaningful. Okay, the idea has always been using the principle of stationary phase. So probably I would. So you start trying to write the stationary phase, very classic. The problem here is that I differentiate, I would get this. and then this lambda is a solution, but that lambda depends on t. So it becomes quite difficult to handle this, and then of course you do some manipulations and etc. And in the end, you could get, so essentially what is it that we have under our control? Somebody has given us this S of t square, that is the envelope. Somebody else has given us the S of lambda square. All that we have under our control are the, if you look at it, the phases that of S of, these are the instruments that we have under our control to get what we want. Okay. So look, this is the thing, and then S of f is given to us. The angle of S of the modulus of S of t is also given to us. What we have is only theta of f and phi of psi of t that needs to be designed. Those are the things that make the equations happen. And if you solve all these, so this is one set of solutions that we are going to get. This is how the domain for final time domain formulation would look like for that particular waveform that we designed. And if you look at it, the envelope is constant, and then everything is going into the phase. You see this, you can recognize this as the LFM waveform, the t square, and then you have all the other things coming up because of the nonlinearity in the system. And then of course you can complete all the I'll show I think the paper is somewhere mentioned. So you will always determine all these waveform parameters based on these functions g's that we were looking at in the beginning. Okay. So what happens is, again, the same thing, that no matter what, we will always have higher side lobes, lower side lobes, wider bandwidth, but then here you are achieving, you are not losing on anything else. So you are getting everything as a what do I say, the constant envelope. You are not losing anything in the mismatch filtering. And then this fundamental problem you cannot avoid. It continues to be the case. So the LFM, it will have the best main lobe, but then you have much higher side lobes. And then you could choose the g's. The g's are the functions that I mentioned. You can choose different g's. I think here you mentioned Han, Ham, and then some custom functions. You can play around with the main lobe and the side lobe levels. You can actually choose the g's based on some design criteria. That here we just chose some g's that we wanted. Again, the question is, you use stationary phase, where we said we didn't compute the complete integral. We looked at the integral in the neighborhood of something where everything was, the space was stationary, and how good is this approximation? So here is the again. Lambda is the pulse width and FB is the bandwidth. So this is nothing but your time bandwidth product. Okay. If the time bandwidth product is very large, infinity, this is what is our the dotted line is what is the energy spectral density that happens. This is what we wanted to design. But if you use a much smaller time bandwidth product, you will see the errors. Roughly, it is following the shape, but you see errors around that. Okay. So it is not a exact solution. There are approximations. There are errors in it. But you can run this setting and then see how good is it for your application. So again, as I said, a waveform makes no sense if I don't have any degree of flexibility. Here I have I just took a waveform with 2 degrees of flexibility, G0 and G1. And then I could vary it, and I could see that the variation in the side lobe levels and then the main lobe width. So the main lobe width goes down as you go from as you increase the G. This is where it's sort of becoming more like the FMCW. And then if you look at it, the side lobe, the peak, the side lobe levels are very small in this region, and then they start going higher as you go closer towards FMCW. So it gives you a sort of trade-off between different things. I would skip this. That was is again the same thing. So this is what we are trying to look at. So waveform is something that is becoming more and more important. Previously was FMCW was one thing that could do everything for us, but now the other thing that I did not mention in FMCW is something called Doppler resilience. So I design a system for zero Doppler. I measure the system, I run the system, I get some SNR. Now the target is now moving at a certain speed. How much SNR do I lose which I don't change anything? So FMCW has this nice rich like thing, so you would not lose much if you have small Doppler changes. Few other things, the PMCW that we designed could have very drastic. It's like a very nice optimization. You go up, any small perturbation, you just go out. Okay. So that is something that FMCW has. You have to look at all these criteria, and then the new applications demand resolution, low side lobes, multiple radars, that means less interference, all these things, and all of them come in nice optimization problems. I did not spend any time on any of the optimization problems, but then there's something that you can try and solve the problems. Then of course you want to do something more data driven. What we did not look at, what we did, all this was only on single radar, single input, single output. And then if you extend it to multiple radars, not only you will have multiple waveforms, but you also have the antenna positions, the array design, everything comes into picture. Then if you go to multiple radars, that becomes another aspect, and then the final thing would be multi-sensor. So you go from multiple levels, and everywhere this waveform, everything comes into picture. Okay, so that is what it is. So sorry for the delay. So it took a bit more time. Then, so thank you.
Thank you, Professor, for delivering an interesting talk. Are there any questions from the audience?
Before you ask, I should say that I am not a radar engineer. I am only a signal processing guy. So if you ask me too many of radar, then I would probably call somebody else.
I'm also a signal processing student, so it's okay. Sir, in the start, you had shown some simulations using ROS. Was it the robotic operating system? And in one of the slides, you had shown like using multiple sensors, we'll need to take the point cloud data to get better clarity about how people are moving in the room.
Yes.
So is that cheaper than the one single surveillance camera if you use multiple radars?
No, camera, as long as you don't, I mean, the idea is different here, right? I mean, I don't know, privacy,
Okay.
switch on the light, switch off the light, I don't know what the camera sees. So, yeah, so those are the things. And these radars are quite cheap.
Yes.
So,
And usually the radars, like on-chip radars, which we are getting, we are only able to detect the IF frequency. So we are getting only the sinusoids.
yes.
So how are you getting the
wanted the
frequency time graphs of the chirps? Because
In which one? The USRP based.
like
No, if I use a custom built radar, the Scotch, the
Okay.
TI and other things, there you don't have access to data, the
chirp.
raw data.
Yes.
But what we also do is SDR, the USRP based transmit receive.
Okay.
There you have you control everything.
Okay.
The only problem there is I cannot go beyond 6 gigahertz or something. The bandwidth is very limited, 100 megahertz or something. So if I want to look at resolution and other things, it becomes very difficult. I need meters of space to do
Yes.
any experiments.
Yes.
So that's why it was more an emulation than an actual validation, what we did. So
Got it.
the raw data or the things were obtained from the USRP based solution.
Okay.
The chirps and everything.
Got it. Got it. So in the second category of the waveforms, which you showed that random for the phases, but the received signal was a clean chirp. Yeah, category 2. Yeah.
Yeah, because the this is what is dominating.
Okay. Okay.
This is what is it is a direct path.
Okay.
So that is what is dominating.
Okay. So the victim waveform has a less SNR compared to the
Yes,
interface.
yes, yes.
Okay.
Because the victim is a two-way.
Ah. Okay,
go
yeah.
and come back.
Right,
Yes,
That's all.
Thank you.
Thanks for.
Thank you for the nice talk. A couple of questions. So I think all top sequences have been shown to have minimum coherence. Have they been used here? These are cubic phase signals.
We did not look exactly at all top. Maybe I should look at that. But what we did was all the other pilot sequences that are used for communication.
Okay.
Because then it's more like easier expansion. The problem we had there was Doppler resilience. So you move all those nice thumbtack responses, you give a certain Doppler, then it's completely lost. So that maybe all top, I don't know, could be good.
And this result is from the 70s.
Yeah,
Altop
should be.
nice paper on optimal sequences for radar. And he showed that cubic phase sequences are actually optimal from the point of view.
From the point of
view of minimal coherence.
in terms of
Or maximally incoherent sequences.
Okay. Okay, so among a set of sequences.
No, he posed it as a design problem. Like you had an objective function and then you came up with the solution. So he had the coherence to be, he wanted to minimize the coherence to delays. So maximally incoherent sequences is what he showed.
Okay, probably I have to check.
Cubic phase signals, and then it's named after him. So your approach, you're still using the MASH filter, right? In the receive, you're using the MASH filter. So it's a linear processing technique, right? But if you could pose it as a parameter estimation problem, would we be able to do a better job of estimating the targets or localizing the targets?
One thing that we have seen is the match filter builds the SNR. So if I want to do something at the next stage, I need to have sufficient signal strength to process the signals. So that was the reason why we sort of, for example, if I want to do a OFDM based radar, I could do a OFDM processing.
Okay.
But it will not give me that SNR that I probably will not be able to even detect the start of the frame. So I need to do because the link budgets are such. So this again, the thing that I don't know if Prof. Chandra is also working on these OTFS and other things. There they go directly to as a design problem, the parameter estimation problem using sophisticated processing. Chandra, you know that better, right? OTF. So that is the thing. Okay, Chandra, I don't know who Chandra now. Yeah, so that is the
depending on where you're beamforming, will respond. By the last question related to the piecewise linear profiles that you got, right? So that's in the design space. You have piecewise linear profiles. Now, what does it translate to in the waveform domain? So ultimately, you need a physical waveform that will have this kind of piecewise linear profile, maybe piecewise cubic or piecewise quadratic. But there are discontinuities. Does it cause problems in the waveform domain?
Yes. So you
ultimately transmit such waveforms. Right?
You ultimately transmit such waveforms. So those discontinuities cause some issues in the waveform design. Yes. Okay. But we sort of did not look so much into that. Then the problem we then sort of started to look at phase continuity. Phase continuity across the things, but the problems are getting quite hard. So it's still under investigation.
Okay. Thank you.
So even the classical FMCW, PMCW sequences, there is no phase continuity. You expect you just run it and then go 0, 1, 0, 1.
Yeah, it was a nice presentation. So my question is that why didn't you directly solve this ISL minimization problem, whatever that is there in some literature, that directly you can get some complicated optimization problem and solve by some technique just to minimize the ISL and get some waveform. Like it was also a waveform design problem.
No, you need some structure to the waveform, right?
Okay.
I mean, I need some structure to the waveform. Something needs to be optimized there, right? So,
okay.
if I just don't do anything, I just put this as a sequence, that is the then you design the sequence elements. Then that is what I did not put anything there. You do all the optimizations, all the various methods. You run it and then you get all the sequences. And the other things, then we started to put a bit more model into the system, so reduce the number of parameters to see if I can get better performance or something else that helps us in our setting. So we did that. So with the parameters.
Thank you.
I hope speaker has answered all your questions. So
No, not a joke.
No, he wants to close the session.
So we have also arranged refreshments at Coffee Hut. Please feel free to continue your discussions there. Thank you all and have a great evening.
Thank you. You close the online session.